Welcome everyone. Welcome to the fourth session of the day. And please welcome Fraser talking about Clevis and Tang.
Hello. Thank you for coming to this presentation, because I know there are many other interesting presentations on all week. This story starts with a hard disk, not necessarily a spinning rust variant of hard disk, but every one of us have one of these in our workstation and laptop, and there are data centers full of these things, and we want to make sure that the data on these things are secure. So that if your laptop gets stolen or tampered with, or someone walks into the data center and yanks a drive out of a rack or yanks a whole rack out on a trolley, and these things do happen, your organization's data or your personal data remains secure. So we use full disk encryption. But, like everything in security and in life, there are trade-offs. So for the security, you have to pay a price. Every time the machine comes up, a passphrase has to be entered, or somehow the system acquires the key material it needs to decrypt the volume encryption keys and read the data on the volume and get on with the process of booting up, or the process of mounting the encrypted volume if you're talking about something that's already after the system is booted. So we want systems, ideally, to automate the decryption of encrypted drives or other secrets, such as TLS keys, or anything else you can imagine that you might want to protect at rest on disk. If you go online, you'll see plenty of people saying, well, I did this whole, get my X509 certificate and secure my web service using HTTPS, but now every time I start the server, it's prompting me for a password, and if the server goes down and comes back up and I'm not around, well, no one will be getting their requests serviced, and that's a problem, so what do I do? And sadly, most of the time the advice is something like this: well, run this OpenSSL command and pipe your key material through that and dump it to disk, and then all of a sudden your RSA keys are sitting in plain text on the file system. So this is also something we want to avoid. This is not good security hygiene, and we can do better. USB drives are another interesting use case. Within an organization, people are still moving data around on USB sticks. Oh, hey, Ahmed, can you get me those big files that you're working on? Yeah, sure, no worries. I'll just put the drive in, and you can have the assets in a moment. I'll just take the disk over, the USB disk. Okay, no worries, plug it in. But then what happens when the employee takes it home in their pocket or loses it? And the reverse situation is problematic as well. Employee finds USB drive sitting on the ground on the footpath outside the office and says, oh, that's interesting. I'll just pick that up, and when I get into my desk, I'll plug it into the workstation and see what's on it, and then you're owned. So it would be interesting to be able to implement a system where within the organization, people can move the data around on USB disks freely, but the disks are encrypted. There's no additional burden on the employees to type in passphrases and so on to decrypt those disks. And anything that comes in that's not encrypted by the company's keys can be rejected, say, no, we're not going to mount that. So not all of these scenarios have good implementations today, but I'm just throwing out possible use cases out there where we have organizations achieving their security goals in a way that's seamless to users. So those are the goals. Let me begin or continue with a demo. So one of the protocols I'm going to demonstrate today and explain how it works is called Tang. I already have two RHEL servers here with a Tang daemon running. So if I do a system control status tangd.socket, we can see, yes, we've got the Tang daemon running, it's listening, everything's all good. So this is a RHEL 8.2.0. This is a development version, but nothing is different in what I'll be showing you from RHEL 8.1, which is out now, or indeed RHEL 8.0. And the same software is available on most Linux distributions. I do not have Tang installed on RHEL 8.2.2, so let me install the Tang package. And yep, let's go. Okay, so that's installed. If we have a look under VARDB Tang, we'll see there's nothing there yet. The socket hasn't been activated, so we can do a system control enable now to have started as well. Tangd.socket. There's still nothing in the Tang database. This is where keys are stored. But if I now ask the server for its key advertisement, and I can just do that with curl. What's the host name? It's whatever it is, /adv. Okay, so I've just queried the Tang server to say, give me your key advertisement. That's the object it gave back to me. And if we have a look in the key database now, we see two keys. One is an encryption key, and the other one is a signing key. Okay, so don't worry too much about all of that. That's just to show how simple it is to install the packages and actually get the Tang server up and running. What do we do with a Tang server? This machine, RHEL 8.2-FDE0, has an encrypted disk, so we can do a crypt setup luxdump dev VDA2 and observe that we have lux2 and the volume is encrypted and there's one key slot and that contains the passphrase encrypted key. If I boot this machine up, well, I might do that right now, connect to the VNC console. In a moment, it'll prompt me for a passphrase to decrypt the volume encryption keys and continue with the boot. So I hope on the video people will be able to see, you in the room can see the bottom line there is prompting me for the passphrase. I enter the passphrase and the boot continues. Okay, so let me just connect to this machine again. What has happened to the network configuration? I obviously didn't sacrifice enough chickens to the demo gods. Yeah, I think it's just come up with a different IP address. That's fine, we can do it all in here. I'm sorry, the text is probably too small. Let me just fix the configuration. NMCLI. So, okay, this will just take a moment. NMCLI, connection modify, that one, IP6. What will we do? 1231.82FDE0. Hooray, okay. So now the important question is, can I actually talk to the Tang server from here? So let me just check. We'll do RAL822, the same one that I configured a moment ago. Oh, several moments now. Yes, excellent. Okay, so what I'm going to do now is do a bind of this system's encryption keys to the Tang server. So it'll be clevis lux bind -d for device, devvda 2, devvda 2, and a pin name, which will be Tang. This is specifying which clevis plugin we're going to use, a bit more explanation on what that is a little later in the talk. And the configuration, which is a small snippet of JSON, which is URL RAL822.ipa.local. Sorry, something's messed up with the console there, but let's run that. Oh, I didn't install the packages. Let's do that first. DNF install clevis and clevis Drakit. Okay, and we'll try that command again. Okay, so it's retrieved the Tang key advertisement. It's saying, do you want to trust the following signing key? So in the default configuration, it's a trust on first use system, but you can also provision offline, and you can also specify in this command and in the other clevis commands the key digests, the digests of the keys that you trust, so that you know that the server you're talking to is not being impersonated. So we'll just say, yes, we want to trust it. We have to enter an existing LUKS passphrase so that it can decrypt the volume encryption key and re-encrypt that in another key slot using the Tang system. So I enter that passphrase. This will take just a few moments. And now if we do a crypt setup, LUKS dump, devvda2, we'll see that key slot 0 is as it was before, key slot 1 is now in use, and down here in the tokens section we have some clevis metadata relating to key slot 1. The final step, because this is a root volume, is we need to rebuild the init RAM-fs to make sure that the bit of code that knows how to understand clevis related metadata and do things according to that data is actually in the boot environment. So we do Drakit-F, and I'll add -v to actually see some output. This will take about 10 seconds. And at that point, I can reboot the machine. I'll switch over to the VNC console and we'll see what happens. Okay, that's done. So let's reboot. Now, over in the console, we're going to see that it will in fact prompt me for the passphrase, but a few moments after that, once the network is configured, the communication with the Tang server will complete. It'll be able to decrypt the volume encryption key and continue with the boot, and that's just happened. Okay. So we'll come back to that server a bit later and do more things to it. But for now, on with the slides. So what we saw there is a demonstration of the Tang protocol. Tang gives you simple provisioning of encryption for secrets. In this case, the volume encryption keys of a root volume. But of course, you can use it on the command line as well to encrypt just any data you give to it. You get automated decryption when the Tang server is available. So the idea is that you'll have the Tang server sitting on your secure network alongside the servers that need to access it, be they employees' laptops or workstations. Once they arrive at the office, they can get the automated decryption. If they're offsite, they'll still have to enter their passphrase. And in the data center, again, behind the firewall, you can have your Tang servers sitting in one rack or across several racks. And the machines in another rack can talk to the Tang servers, and the encrypted volumes can be automatically decrypted. The clever thing about Tang that makes it different from, for example, a general key escrow system is that the secret never leaves the client. So the Tang server doesn't look after any secrets. In fact, it's, other than the keys it knows about, completely stateless. And instead, it's a key computation protocol where only the client can compute the key, but it requires the cooperation of the server to recompute that same key each time. So the assumptions here, the security assumptions, are that the Tang server is only accessible from or within this secure network, that secrets and keys are safe in the client's memory, although this is no different from the assumptions you have for any full disk encryption system, and that there is sufficient entropy available on the client side at both provisioning time and every decryption time. So, to get into the details of how this works, there's going to be some math. It's fine if you don't understand this. You don't need to understand the maths of how this works in order to understand how to use this system or the benefits that it gives. But for the cryptography wonks in the room, you're going to enjoy this. So Diffie-Hellman is a key agreement protocol. We say key agreement, sometimes you might hear key exchange. In the case of Diffie-Hellman, in the case of Diffie-Hellman, the keys are never actually getting sent around, but rather some public information is being exchanged such that two parties can compute the same secret that they then share. They share in the sense that they both know the same thing, not in the sense that anything has gone across the wire to convey that secret directly. So we, in cryptography, use Alice and Bob when talking about two parties who want to communicate, and Eve is the eavesdropper who can see all of the public information that Alice and Bob are exchanging. The goal is that Eve will not be able to learn or compute the secrets that Alice and Bob are then relying on to secure subsequent communications. Diffie-Hellman parameters are a cyclic group, and we use the notation G of order n with some hard problem. The most well-known is the group of integers, the multiplicative group of integers modulo p, where p is prime, and that's the discrete log problem, is the hard problem for that group upon which the security lies. We talk about a hard problem because there is no known algorithm to efficiently perform the discrete logarithm on conventional computers. Elliptic curve cryptography uses elliptic curves over finite fields, and the hard problem there is point factorization. We then have a generator element of the group G, and a generator is just a single element of the group which you can raise to different powers to eventually compute every single element of the group. Hence, it generates the group. Okay, so these are the parameters of Diffie-Hellman. How it works, let me use the pointer here. So in step one, the client and the server, or the two peers, both pick a random number between 1 and the size of the order of the group, so the number of elements in the group. They never share that number, but they take the generator, they raise the generator to the power of their private key, and these become the lowercase a and b. These are the public keys. The client and the server, or the two peers, exchange public keys, and then on either side they raise those public keys to the power of their private keys and arrive at the same value. Anyone who possesses any or all of the public information in this protocol still cannot compute the secret that they share. So that's how Diffie-Hellman works. And protocols like TLS rely on Diffie-Hellman in order to, there are variants or cipher suites in TLS that don't, but typically Diffie-Hellman or elliptic curve Diffie-Hellman is used these days. The integrated encryption scheme is an encryption algorithm based on Diffie-Hellman. You can imagine Alice doing sort of her half of the Diffie-Hellman and then sending along the message encrypted with the shared secret that at that point isn't shared, along with her public key, and then Bob can decrypt the message. And in the integrated encryption scheme, the symmetric key used to encrypt the main message that is being sent, what we would call the plaintext, is derived using a digest of some serialization of the private key, the shared secret. And so Bob can decrypt the message and eavesdropper cannot. So now we come to McCallum-Rallier exchange, and this is what the Tang protocol is built upon. So it's an encryption protocol based on Diffie-Hellman and IES, and it's due to Nathaniel McCallum and Bob Rallier, who both work at Red Hat. And Bob Rallier is a cryptographer, and Nathaniel McCallum's a software engineer working in security products and applied cryptography. So in McCallum-Rallier, Alice encrypts a message to Bob's public key, but doesn't send the message. The message is the volume encryption key, for example, in the demo that I did earlier. To decrypt the message, Alice asks Bob to encrypt an ephemeral key and then uses the reply to recover the original secret and proceed with decrypting the message. So an eavesdropper can't decrypt the message, and neither can Bob. In this case, Bob is the Tang server. So the Tang server can never compute the secret that is used to encrypt the volume encryption keys or whatever data it is that you're securing at rest on the client side. So the parameters, the group parameters and order and all of that is the same as Diffie-Hellman. We also have the key derivation function, for example, SHA-256, and a symmetric encryption algorithm used to encrypt the message and the message. So for the provisioning step, at 1, just as in Diffie-Hellman, the client and the server both generate a private key. The server's private key is long-lived. The client's private key is per message to be encrypted at rest. So these are not ephemeral keys. The server transmits its public key to the client, and this can be done as an offline step. This doesn't have to be online. At step 4 here, the client computes the G to the AB, what in Diffie-Hellman would be the shared secret, but in this case, only the client ever learns it. Derives a symmetric key from that. At step 5, uses the symmetric key to encrypt the message, and then stores on disk the client's public key and the ciphertext, and then at step 6, throws away the private key, the client's private key, and the session key that was used to encrypt the secret. That's the provisioning step. So at this stage, the only thing left on the client is the client's public key and the ciphertext. for the decryption step. And this is why we need good entropy every time a decryption is to occur, including at early boot, if you're talking about a root volume. An ephemeral private key is generated in the same way that the public and the private keys for the provisioning steps are generated. The client then multiplies the public key by the public key corresponding to this ephemeral private key, X, and it then transmits that X to the server and says, hey, do some math on X, please. The server raises X to the power of the server's private key B and transmits the result back to the client. And here's where the magic happens. The client can now compute, using X prime, the original secret that was used to encrypt the data. So again, it applies the key derivation function, derives the same symmetric key, and gets on with the job of decrypting the message and using the data. So using the, in our demo, the volume encryption key, but basically decrypting the secret, whatever the secret is. So that's how it works. The Tang implementation of what you have seen today is a server-side daemon and a Clevis pin, which is a plugin for the Clevis system. It's written in C, it's small and fast, it has an extensive test suite. The messages are JSON and Jose objects in terms of what's going on the wire in the protocol, sent over HTTP. There's no TLS, it's not needed. It's basically something like Diffie-Hellman, so all of the messages can be public. As we saw in the demo, in the default configuration, it's a trust on first use system, and the key signing allows the server to rotate its keys periodically. And the offline provisioning is possible because the only thing the client needs to encrypt its data is the server's public key, which will be, long-lived, for some value of long, according to whatever key rotation regime is appropriate for the organisation deploying this. So the threats are a man in the middle or a impersonation during provisioning. This would essentially be a denial of service against the client, in that it could encrypt to a bogus Tang server that will then go away and no longer exist, and then your automated decryption cannot work. The Tang server itself is a DOS target. I mentioned already you need good entropy for the ephemeral key X, including at early boot if that's what you're using this for. And Diffie-Hellman, elliptic curve Diffie-Hellman, all these hidden subgroup based crypto schemes are vulnerable when quantum computing becomes practical. There's a Diffie-Hellman analog that's quantum resistant called supersingular isogeny Diffie-Hellman that might become a practical crypto system. I don't know too much about it, but I'm sure by the time quantum computing can practically attack these systems, fingers crossed, there'll be a valid alternative. So, mission accomplished, right? Well, no, not really, because there are lots of other things we might like to bind secrets to, and we haven't really reached our goal of being able to implement unlock policies driven by organisational needs. So you might want to seal secrets into the TPM of your laptop so that if someone yanks the disk from your laptop, you can no longer decrypt it. Smart cards are another good option. Maybe you want some sort of physical proximity-based decryption system, potentially based on Bluetooth. You might have an escrowed master key of last resort, so that if your employee gets hit by a bus or there's some other catastrophic failure, you can go down to the vault and pull out the keys and, as a last resort, decrypt it. Biometrics? Maybe. I don't know enough about them, but maybe it's possible. So security is not binary, and the policy should be driven by business needs. So we ask the question, can we support these arbitrarily complex unlock policies? The answer is yes. We use a protocol called Shamir's secret sharing, or an algorithm, I should say, called Shamir's secret sharing. To describe the first point, k points describing a polynomial of degree k minus 1, to put it in layman's terms, to describe unambiguously a straight line or linear function in a plane, how many points do you need to know? 2. 2 points. 3 will describe unambiguously a parabola or a quadratic function. 4 will describe a cubic function, and so on. This is the principle upon which Shamir's secret sharing is based. So for however many shares you require as the threshold for recomputing a key, you need a polynomial of degree 1 less than that. So you construct this polynomial. You take the value of that polynomial at however many points you need shares to distribute, as long as those points are not 0, because the value of the function at 0 is the secret. So you can distribute as many shares as you want. So for example, if you have a quadratic function, you need 3 shares to recompute the secret, the value of the function at x equals 0. But you can distribute as many as you want. So if you distribute 6 shares, then you need 3 of those 6 to recompute the function and learn the secret. This is used, for example, for securing the DNSSEC root keys. I think they're broken into 7 shares or something like that, and you need 3 or 4 of them, and they're in vaults all across the world, something like that. Okay, and you use a Lagrange polynomial to recompute the value of the function at 0. You can read about that on Wikipedia. I'm not going to show the math here, but it's really cool. So with the power of Shamir's secret sharing, we could now implement a policy like this, assuming we had Clevis plugins for all of these things. So you could say, starting from the right, we require either the master key that was archived away in the vault, or the key that has been computed as a result of the Shamir's secret sharing configuration that requires both of the TPM and the result of the Shamir's secret sharing configuration that requires 2 shares of something stored in a smart card, or a password, or the Shamir's secret sharing configuration that requires 2 of the 3 Tang servers in the organization. Something like that. So you can devise these sort of elaborate hierarchical key unlock policies according to the security needs of your organization. So Clevis is the client-side pluggable key management system based on Shamir's secret sharing. The plugins we call pins. We currently have 3 pins shipped and supported in RHEL and other Linux distributions. Well, not commercially supported, but the same software is in them, so yeah. We have Tang, TPM2 pin, and the Shamir's secret sharing pin. It uses JSON configuration, and Clevis also is implemented in C and uses OpenSSL primitives. So, a demo of the Shamir's secret sharing stuff. So, where are we? Okay. Oh yeah, the IP address changed again. How lovely. NMCLI. Okay. Hooray. So, .json. So here's an SSS policy that requires 2 of the 3 Tang servers on the network and a secret seal to the TPM. I wish I'd done a diagram to show this better, but hopefully you get the idea. So we require the TPM secret and 2 of the 3 Tang servers to be up and running, and this allows for some redundancy, maintenance, or transient issues in the network to hopefully not affect the ability to automatically unlock. Now I'll do a Clevis encrypt on the command line. So yeah, echo top secret through to Clevis encrypt SSS, that's the top level pin in the policy, and then the configuration. And we'll write that out to, oh, don't do that to me. Copy pasta. Okay, so it's going to prompt me to see if I trust these keys. So now this is talking to all 3 Tang servers, which are running on RHEL 8.2.0, RHEL 8.2.1, and RHEL 8.2.2. And that's encrypted. The output is a JWE, JSON Web Encryption object. Yep, there's some JSON things in there and some base64 serialized binary data, and yeah, I won't subject you to an anatomy lesson. But if we do a Clevis decrypt on that, what did I call it again? TPM, no, tang3 tpm.jwe. That'll decrypt automatically, and we see the secret was the string top secret. Now let me bring down one of the Tang servers. So system control stop tangd.socket. So I'll bring down RHEL 8.2.2 and let's run the decrypt again. And we'll see we did get one message on standard error there saying error communicating with the server. So it tried to talk to one of the Tang servers, RHEL 8.2.2, and failed. But it was still able to decrypt the secret. And if we bring down, say, RHEL 8.2.0, well, now we've got a problem. We can no longer decrypt it because there's only one Tang server and we required 2 of the 3 to be up and running. And I could rebind the LUX volume. All the Shamir secret sharing and the TPM pins are also supported in the initram FS for the encryption of root volumes. But I think I'll just go through the rest of the slides and then I'll answer your questions, and then if there's time, I could show you that later. So, in regards to the LUX integration, LUX v2 has the full Clevis support. LUX v1 had direct Tang support only. And it could talk to, I think, 1 Tang server only. Don't quote me on that, but in any case, everything's moved to LUX 2 in the recent releases. So we have the full Clevis support. We have the Drake unlocker for early boot decryption of the root volumes. We have a system D unlocker for late boot decryption of non-root volumes, and the UDISC2 unlockers for decryption of volumes that arrive and depart throughout the general use of the machine, for example, USB sticks. The history of the project, this all started around almost 5 years ago now with the DAO project, from the Greek to bind. It used TLS for privacy in the channel between the client and the server, and an X509 encryption cert. And as much of an X509 wonk as I am, that's the main thing I work on. That's a whole lot of unnecessary complexity. And the server was decrypting and returning the secret to the client. So the server is learning the secret, and we lose those nice security characteristics that McCallum Raleigh gives us. Well, later that year is when the McCallum-Raleigh protocol was discovered by McCallum and Raleigh, and as soon as it was, we recognised its beauty and its potential, and the rewrite began. And shortly after that, the project was split into Tang, which is just dealing with the McCallum-Raleigh bits, and Clevis, which is the client-side framework for the implementation of the hierarchical key policies. It's available in all the common, well-supported Linux distros. The source code is up on GitHub under GPL v3, and you can definitely help by trying it out and filing bugs, telling us about your use cases and what kinds of key unlock policies your organisations think would be useful to help you meet your security goals. Clevis pins can be contributed. As I said, we only have the TPM2, Tang and SSS keys at the moment. We used to have a password key. We actually got a password pin, sorry, I should say. We got rid of that because in the early boot, when you have LUKS prompting you for a password and then you have a key policy that possibly has multiple passwords in it, it's a tractable problem, but we just punted on that to work out later. But as you saw, LUKS still prompts you for a password, which it will then use to try to unlock any of the key slots. So you can still use a password. Implementations for other operating systems would be great, and if you're playing around with it, by all means, blog about it, post a tutorial or a demo, go and talk at conferences, etc. And the terminology, as the final point, a Tang and a Clevis is a primitive kind of shackle, and the pin is the thing that holds it all together. Links there to the GitHub organisation and the RHEL documentation, which is fairly comprehensive and useful. These slides contain some links. The slides are up now on speakerdeck.com/FraserTweedale. Thank you for your time, and if there are any questions, we have a few minutes for me to answer.
We have time for a couple of questions. Just raise your hand if you want to ask one.
Thanks, Fraser. In practice, if you're bringing up a web server that had multiple secrets that needed to be decrypted, like volume partitions, TLS keys, maybe database credentials, do you run into entropy problems if it's trying to bring up all of those things at once?
Well, you're not typically trying to bring them all up at once. It's really only in early boot when you're likely to run into entropy problems, because modern versions of the kernel collect entropy from all kinds of reliably random sources, like packets that are arriving on the network and so on. So I don't think it's likely to be a problem in practice.
Thanks for the talk, Fraser. You did a good job of explaining a pretty complex scheme. Do you run it on your laptop?
No. Well, only on the VMs on my laptop that I use to demo it to people.
So when you're building this in a large scale, you've obviously got multiple Tang servers around the place. Do you do any, I guess the assumption is that all of the machines have to talk to all of them at one point, or would you replicate that data set?
So each Tang server will have different keys.
Yeah.
And with the use of Shamir secret sharing, you can have the threshold saying, oh, well, we only need to talk to so many of the Tang servers that are, were at one point accessible within the organisation. We don't have anything in the implementation right now to say, well, let's only try and contact, the threshold machines to make sure that we're not just spamming, 20 different machines all at once when we don't need to get answers from all of them to unlock the secret. So that's something we could potentially look at in the future. But I mean, I don't think you would typically want to implement a policy where you really need to hit a lot of Tang servers to decrypt the secret.
We got time for two more. We'll get 3 hands. Okay, let's go.
just to follow up on that, you can't cut it down to the point where you could have redundant Tang servers, but you only require one of them, though, right?
You can definitely require only one Tang server. Yeah.
Out of a set of.
Yeah, you could have one out of n for any value of n.
Okay.
Yep. Up to however much metadata you can stuff in the LUKS key slot or the LUKS headers.
Thanks for that. Is the key exchange, do you know if that's FIPS compliant?
Good question. Yeah, the answer is I'm not sure. We're definitely using only primitives that are FIPS compliant. In terms of the fact that this is a network protocol, I don't know what FIPS would have to say about it. But it's a good question, and I can follow up with the security and compliance teams and get an opinion on that. But yeah, all the primitives we use would be FIPS compliant.
How does the Tang server store its private key?
You win, Nick. Well, let's see. It's in the clear, so hopefully your Tang server is using full disk encryption and perhaps talking to other Tang servers to automatically decrypt itself. Yeah, absolutely. That's not implemented, but yeah, there's no technical reason why you couldn't or shouldn't.
All right, thanks, friends. There you go.
Thank you.
Another big round of applause for Fraser.